So Green's theorem. So this is Green's theorem here, basically, that the idea is if you have a curve, a closed curve, so what that means is that it comes back and touches itself, okay? And another important thing is, so it has to be closed, and it also has to be what we call positive orientation. And positive orientation is counterclockwise. So it has to be this orientation, like that. If it's not that orientation, that's okay. It's just, if it's not that orientation, then it's the negative. Okay, so if you reverse, if you take the same integral the opposite direction, you get the negative of the original. Okay. But if you have p dx plus q dy, and you're doing a lat in a line integral, that's going to be equal to the area integral. So you can, instead of taking an integral around a line integral around this curve, you can calculate that line integral by taking the area integral inside. Okay, so that's kind of a useful theorem. Sometimes people tell me that if you do a job interview, then this is one of the things they might ask, hey, do you know Green's theorem? And then if you can answer that, then maybe you'll have more chance of getting the job. Okay, maybe you have less chance of getting a job, who knows? Probably more chance though. Okay, so let me give you an example here. So we have a line integral, we're going to do it in two ways. So the first one is directly, and the second one is using Green's theorem. Okay, so this would be like the left-hand side. This would be like our P, and this is our Q in Green's theorem. But we're not going to use that right now. So over here we have the curve that we're going to go around. See, it's counterclockwise around the triangle. Okay, so it's a triangle. The vertices are 0, 0. So there's 0, 0. 1, 0. So here's 1, 0. And 1, 2. Okay, so here's 1, 2. And so it's this triangle. And it says counterclockwise, so that's the positive orientation. So it's going around this way. And we're just line. And so what you're going to have to do is probably split it up into 3 pieces. So the first one will be this right here. It'll be this curve right here. Okay, so number 1. So if you're going to do the integral, then we have to find a parameterization. And so R1, so for this one, this parameterization will work if you do T0. Okay, because when T is 0, you get 0, 0, and then when T is 1, you plug a 1 in there, you get 1, 0. So that will work for that one. And then we have a second one, which will be this one right here. Okay, so you start here, go there, then you come up, then you're going to go up here. And the parameterization for that one could be, oh dang, I didn't leave very much space for myself here. I'm going to do it over here. Okay, so you want to start with that point and end at that point. Okay, so you can apply the formula. This is what you're going to get. You get 1, 2t. I'm using the same variable t. Okay, so notice that if I put a 0 in, I get 1, 0, which is that point. And if I put a 1 in, I get 1, 2, which is that point there. And then this third one, and for that one, I have 1 minus t, 2 minus 2t. Okay, so in general, that's just basically applying this right here. You go 1 minus t times the first point. Okay, plus t times the second point. That's basically t times the second point. So that's basically how you get t, and then simplify it, okay? So, and notice I put a 0 in for t, you get 1, 2, which is that point. And if you put a 1 in, you're going to get 0. Both those are going to 0 out. Okay, so you have those three right there. And so this integral is going to be, you split it up into 3 parts. So we're going to go over the first one, and that goes from 0 to 1. So this is r1 of t. So going over the first one. So xy, so this is our x, that's our y. So that's going to be t times 0. Yay, that's good. And then dx is 1. Okay, and then x squared y, so this is x squared is t squared, and then y is 0, so that's 0. Okay, and then dy is 0, so, okay, so that's just going to be 0. Okay, that's the first integral. The second integral, which is this one, which is this right here. Okay, so r2 of t. Okay, xy, so that's going to be this times this, so that's 2t. And then dx is the derivative of this, which is 0, so that's 0. That's good. And then you have x squared y cubed, so x squared, that's 1, and then 1 squared is still 1, and then 2 cubed, 2t cubed, and then you're multiplying by dy's, and then you're multiplying by 2. Ah, dang, that's not 0. Oh well. That's okay. And then you have the third one, which is this one right here. So xy, that would be this times this. Dang. Times dx. So this is, okay, so dx would be -1. So I'll throw a -1 there. Okay, and then for this piece, you have x squared. So that's 1 minus t squared times y cubed, so that's this cubed, times dy. And this is, dy is -2. Like that. Okay, so great. That's all 0, and that's all 0 too. But here we have what is that? 16 t cubed. Okay, and then this one, this is tricky. So that's -2 times 1 minus t squared. That's the first piece right here. And then here, we can factor a 2 cubed out of this. And so then that's a -2 right there. So that's -16. And then we'll have 1 minus t to the 5th power. Okay, great. So now we can integrate, and this gives us 4t to the 4th. I guess they're all integrating from 0 to 1, so you can just all put it together as one integral. And then the integral of this one is 1 minus t to the 3rd power. It's like that. Okay, because when you take the derivatives, you get a 3 coming down and cancels that out. And then the derivative of the inside, and this reduces to 2, which is right there, and then the inside gives you a -1 kicking out right there. Okay, and then this one 1 minus t to the 6th power. And it's over 6. Well, there's negative 16. There's 16 right here. But there's a negative. The negative comes out. This negative comes from here. Then the derivative of that is the inside. Okay, and so you're going to evaluate that from 0 to 1. So putting a 1 in, you get 4, and then those are both 0. And then putting a 0 in, you get minus 2/3, and then minus 16/6, which is 8/3, which turns out to be, in the end, 2/3. Okay, so that was the first one. That was the first way. And now we're also supposed to do it using Green's theorem. Using this Green's theorem. Okay, so Green's theorem, what we're going to do is we're going to take the integral inside here. Okay, and this curve is y equals 2x, right? Okay. So Green's theorem says that the integral is going to be the integral over the region of partial of q with respect to x minus the partial of p with respect to y dA. Okay, so we're integrating over this region. Let's first figure out what partial of q with respect to x is. What is that? So here, this is our q, right? So what's the partial of this with respect to x? That goes right here. What's the partial of this with respect?
X cubed over 3 y cubed.
2x y cubed. Right? And then the partial of p with respect to y is going to be what? So there's p. The partial of this with respect to y is just going to be x, right? Okay, I'm going to integrate with respect to y first and then x. So if it's with respect to y, then this lower curve is y equals 0, so I can put 0 here. And what do I put up here? What goes right here?
1?
No, this is in y. What's the boundaries on y? I said the lower boundary is this. The upper boundary is this. The idea is you want to draw a vertical line segment. And it hits the lower boundary here, it hits the upper boundary here. The lower boundary is y equals 0. The upper boundary is y equals 2x, right? So it's going to be a 2x there. And now, you're right on this one, the x's goes from 0 to 1. Okay, so x's goes from 0 to 1. Okay, so here's our integral that we need to find. And hopefully we have enough space for that, I guess. Let's see here. So if we take, I'll go one more here. Okay, so now we can integrate in y, and this is going to be, let's see, xy to the 4th over 2 minus xy. That's integrating in y. And that goes from y equals 0 up to y equals 2x. Okay, I plug in 2x for y. That's going to be, well, that's going to be 16 over 2. That's going to be 8. X to the fifth. Okay, all that be, so the y gets replaced with a 2x. So you're going to have x to the fourth and an x, that's x to the fifth. And then this is going to be minus 2x squared. And let's see, so that's going to be 8x to the sixth over 6 minus 2x cubed over 3. 0 to 1. So you plug a 1 in, that's what, 4/3 minus 2/3. And you plug a 0 in, that's going to be 0. So again, we get 2/3, which is the same as that one. So this is the same. So technically, we could have just put the same answer in both slots and we got it right. Because, you know, that's Green's theorem. They're supposed to be the same answer. Okay, so that's kind of interesting. We do it two seemingly completely different ways, and you get the same answer. Green's theorem is sort of like the fundamental theorem of calculus, but for 2 dimensions. And so in 1 dimension, okay, in 1 dimension you're integrating across down this line, right? And you're just taking, and then you have boundary points. So you're integrating from A to B. And so fundamental theorem of calculus says that your integral is just going to depend on the boundary points, those 2 boundary points. Okay, so likewise, this integral over the inside, or the inside here, only depends on the boundary, just the boundary points. But it can be used both ways. It can be used for finding the line integral that goes around, or for finding the integral, or for finding the area. So sometimes, so in this case, which would you say was easier, this first way or the second way?
Probably the second way.
Yeah, the second one was much shorter, right? And we didn't have to do 3 parameterizations of curves, right? So the second way was easier. And a lot of times that's going to be the case. Or perhaps even the second way is possible, whereas the first way is impossible. But then also the other thing could happen. The area, this could be much easier than this one, okay? And so then we would want to calculate something like this. We would want to calculate an integral like that instead. So we just have to keep that in mind. Okay, so Green's theorem, which I've copied down here on the number 2. Okay, so number 2, use Green's theorem to evaluate this integral. And C is the circle. X squared plus y squared equals 4. Okay, so you're integrating over this circle here. What's the radius here?
2.
Yes, that's 2. So, and the center is at the origin. So here we go. Okay, so, and then it doesn't say the orientation, but we're just going to assume it's the positive orientation, the clockwise orientation. And just assume that if that's the case. Okay, so the integral, this integral is going to be equal to the integral over this region here, D, of dq dx minus dp dy dA. Okay, so what is dq dx? Okay, so here's q, right? So dq dx would be
negative 6 x to the second.
yes, and then dp dy. So here's p right here.
Be 6y.
Yes.
Squared, sorry.
Okay, now if we're integrating over this circle, then we should probably use polar coordinates, right?
Right.
And r is going to go from 0 to 2. So keep that in mind. The radius was 2, so we've got to keep that in mind. R is going to go from 0 to 2, so dr. So r dr d theta. And theta is going to go from 0 to 2 pi, right? That gives us the whole circle. And what does this become? Well, that's negative 6 times s squared plus y squared, right? And what's x squared plus y squared? In polar coordinates. Okay, that's r squared. So that's a negative 6 r squared. So this inside part just became negative 6 r squared. Okay, now there's no, okay, so just noticed there's no thetas anywhere, so I can just take the difference here. That's just 2 pi. And then I'm going to integrate, what's this, negative 6r cubed dr. I guess I can do some canceling. So the 4 reduces to 2, and that reduces to 3, and then this is 2 that goes away. So this is going to be pi times, or negative pi times 3, and then times 2 to the 4th. So 16 times 3 is 48, so negative 48 pi. Okay, any questions about that? Let's go on to the next one. Okay, so here, this, so C is the curve y equals cosine x from negative pi over 2 to pi over 2 0 to pi over 2 0. And then the line segment from pi over 2 0 to negative pi over 2 0. So this is what it looks like. So negative pi over 2. The cosine comes up here to 1, right? And it goes down. So this is y equals cosine x, this top curve here. And then this is pi over 2. So what's happening is you're going to take the curve from negative pi over 2 up over on this hump right here. And then you're going to take the line segment back. And they give you a hint here. Check the orientation of the curve. Okay, so what do you notice about this, about the orientation of the curve?
Along the x-axis is negative. I don't know.
Yeah. Okay, so is it clockwise or counterclockwise?
Oh, it's clockwise.
Okay, and and you guys know what I said about that, what that means? It's negative orientation. Okay, that's negative orientation. So I said Green's term applies when you have a positive orientation, which is counterclockwise, but it doesn't really matter you can still apply Green's theorem. It's just that because essentially what happens is if you have a negatively oriented curve, so we can write that way. That's equal to the negative of it as if it was positively oriented. Okay, so it's like, essentially this is like integrating from B to A instead of going from A to B. Okay, from going from a larger value to a smaller value instead of going from a smaller value to a larger value. That's basically what it is, what the orientation is. Okay. So let's go ahead and do it. So it's f.dr. So it's basically, that means it's e to the negative x plus y squared dx plus this one, e to the negative y plus x squared dy. Okay, so that's what we're integrating. Now, according to Green's theorem, okay, so this is our P and this is our Q. Now, this is going the opposite direction, so we're going to add a negative to get, so this negative right here, this is from, that negative is from the negative orientation. Okay, and then we're just not going to worry about the rest of it. Apply Green's theorem. We're going to integrate over a region, and what are we going to integrate? So now we're going to integrate over this region right here. dq dx, what's the partial of q with respect to x is what? There's q. Partial of this with respect to x is just, that's 0, right? So it's just 2x. And the partial of this with respect to y, so minus the partial of this with respect to y, which is what, 2y? Okay. So what, okay, so if I go dy dx, what's the boundaries on y going to be? What are boundaries on y?
0 to cosine x.
Yes, 0 to cosine x. So this is the upper boundary, and then the lower boundary is 0. And then x goes from
Negative pi over 2 to pi over 2.
exactly. Dang, I'm confused. Oh well. Okay, so integrating this in y, we get 2xy minus y squared. and that's going to go from 0 to cosine x. And so this is y equals cosine x. So this is 2x cosine x minus cosine squared x dx. That's plugging all that in. Now antiderivatives, this is going to be, this one is 2x sine x plus 2 cosine x. You take the derivative of that, you get that. And this one is 1/2 x plus 1/4 sine of 2x. Hold on a second, I'm a little bit confused about this. Okay, so anyways, you're going to get, okay, so if I put a pi over 2 in, if I put a pi over 2 in here, I get 2 times pi over 2. Sine of pi over 2 is 1. That's going to be 0 both ways, and this one's also going to be 0, because when I put pi over 2, it's going to be pi, and this is going to be negative pi, so that's just going to give me 0. And then pi over 2 in here gives me pi over 4. Dang, now I'm really confused. I am just like super confused. Oh wait, I know. No, I'm not confused now. I know what I made. I know what I did wrong. This is minus, and that's minus. Okay. So this is minus. Okay. And then when I put negative pi over 2 in, I have 2 times negative pi over 2 times sine of negative pi over 2 is negative 1. And then minus a negative pi over 4. Dang, I'm still confused. So what do we get? We have pi. What? Oh no. This right here and this right here are just going to cancel. These are the same, right? But this is a minus. So those are going to cancel. And this is minus, there's 3 minuses, so it's minus pi over 4. Okay, so the answer is pi over 2. Okay, so great, that was number 3, so that's pi over 2. Any questions about that? So the important thing we had to add for the negative orientation there. Okay, so number 4. Okay, for this one, this is kind of interesting because this is just sort of an application. I'm only gonna put this in the homework, not in the exam or anything. But so you have these line integrals right here, and it's equal to the integral over an area. And okay, so if this is 1, then it's the area of the region D. It's the area of the region D. If this turns out to be 1, and there's different ways it can be 1. So like here, this is our Q, right? And so partial of Q with respect to X minus the partial of P with respect to Y, that's going to be 1, right? Because the partial of this with respect to X is just 1. So that's going to be 1 minus 0, so it's 1. And so that means that so you have these two equations right here, and the idea is you're going to set, well, first of all, I'm going to set 1 minus cosine t equal to 0, and which is the same as cosine t equals 1. And then, so the two values are t and 2 pi. Okay, so that means that when you're at 0 and when you're at 2 pi, then that's when the y component is going to be 0. Okay, and then the x component is t minus sine t, and when t is 0, we get 0, and when t is sine t, you get 2 pi. So that also matches up with, so the x component also matches up with this, okay? So t component and x component are both 0 here and 2 pi there. So this could be the x-y-axis or it could be the y-t axis, either way. Okay, and so then as t increases from 0 to 2 pi, 1 minus cosine t is going to go up and then come back down like that. And so the objective is if we go like this, okay, then we want to find the area. So we use Green's theorem. So here's the area this time right here, right? And as we went over before, if you could just make this 1, then this integral here is going to be the area. If you could make that minus that equal to 1. And these are different situations that actually do that. So if x is, so for example, if q is x, then dq dx is 1. And then dp dx is just 0, okay? Because there's no dx part. Now, if this is the dx, then this is our p. So this would be p, would be x, and then dp dy would be 1. Okay, and so if you put a negative on the front and you have this as 1, then you have a negative on the front, and then it's minus 1. So 0 minus 1 is going to give you 1 also, or it can just kind of do a split of the two. So I'm going to choose this option here, though. So for the area. Okay, so the area is going to be the negative of the line integral around the curve of y dx. But also this is negative orientation. Okay, so you remember that positive orientation was counterclockwise, and this is clockwise, so this is negative orientation. So that means we're going to add another -1 on there as well. Okay, so we have, so there's this negative here, but then there's also a negative because we're going negative orientation. Okay, and then this part right here, we'll call that C2, and we'll call this part of the curve C1. So this part's C1 and that's C2. So the integral, so these negatives are going to cancel out. And so you're going to get the integral over C1 of y dx plus the integral over C2 of y dx. Okay, but for this one, y is 0 for the whole curve. Okay, so here y equals 0 for the whole curve. So that means that this is just going to be 0. That goes away. So we're only left with integrating over here. And we have y is this and x is that. And so it's going to go from 0 to 2 pi. We know that already. And then y is 1 minus cosine t. And then here your dx is going to be 1 minus cosine t dt. Okay, so you're taking the derivative of this gives you that. And then that's going to go okay, so this is going to go down into here. Okay, so integral from 0 to 2 pi of, we expand all that out, you get 1 minus 2 cosine t plus cosine squared t. And integrating, you get t, the integral, that's t. The integral of this is minus 2 sine t. And then the integral of this piece is 1/2 t plus 1/4 sine of 2t. Okay, and now it's going to go from 0 to 2 pi. Okay, if you put 2 pi into here, or 0 into here, you get 0, so that's gone. And that's also gone as well, because if you put 2 pi in here, you're going to get 0. If you put 0 in, you get 0. Okay, so all that's gone. All that's gone. So I only have this right here. And that is, well, that's 3/2 t, but then you put a 2 pi in for t, so you get this, so you have 3 pi.